Hi, and welcome to another episode from Spiral Physics Education. I'm going to be looking at calculating acceleration and another equation of motion in this episode, and specifically using the equation for acceleration and change in velocity over time, and also how to use this very specific and on the surface complicated looking equation, v squared equals u squared plus 2as. So it's quite a mathematical episode. So what you need to know to get the most out of this lesson will be something to do with vectors and scalars and some examples of each, and how to calculate velocity and know that it's a vector. And then going straight onto acceleration, I'm going to be looking at the definition for acceleration. And definition for acceleration is the rate of change of velocity. And this rate of change statement comes up a great deal in physics. And if acceleration is the rate of change of something, then that's what rate of change means. It just means it's something divided by time. And the rest of it says is velocity, so what that really means is acceleration is change in velocity over time. But a fancy way of saying it is the rate of change of velocity. Just in case you're not sure, change in velocity is final velocity minus initial velocity. Sometimes it's written as a delta v, delta meaning change, so delta v is the change in velocity equals v, the final velocity minus u, the initial velocity. So those are symbols commonly used in equations that you will see in physics for this topic. And if you put that all together, you might see acceleration as delta v over t, so delta v is change in velocity over time, or you might see it as v minus u over t, and again v final velocity, u initial velocity, and the time between the two. So all of those are different ways in which this equation could be presented to you. So we're looking at the difference between acceleration and deceleration as well. But be careful that it's not de-acceleration, it's deceleration. We need to have an idea about what's the difference between acceleration and deceleration. Well, it's all to do with how the relationship between velocity and acceleration in terms of their direction, because they're both vectors. So let's say that the velocity is acting to the right, and I'm going to consider that to be a positive direction. And let's say that there's an acceleration also acting to the right, which is also positive. If the velocity and the acceleration are acting in the same direction, then we call that acceleration. That means that the velocity will increase. The object is going to accelerate. So for deceleration, let's assume that the object is still moving to the right and that that's a positive velocity. But this time, let's say that the acceleration is a negative acceleration, and that means it's moving in the opposite direction. And if the velocity and acceleration are acting in the opposite direction, that's deceleration. So that acceleration, that negative acceleration, will make the velocity smaller and smaller and smaller. So we call that deceleration. So let's have a look at an example of calculating acceleration. So we've got a car that starts from rest and it reaches 20 meters per second in 4 seconds. And we're going to calculate the acceleration. So as usual, we quote the equation to start off with. And sometimes these equations or the questions can get very complicated, so it's sometimes nice to highlight them and identify which parts of the question relate to which parts of the equation. So we've got the word rest here. That comes up quite a lot in physics, and students often sort of glaze over it and don't really appreciate what it actually means. But rest means that u, the initial velocity is 0. 20 meters per second is the final velocity v, and the time is obviously 4 seconds. So once we've identified what all the different variables are in there, all the physical quantities are, we get 20 minus 0 over 4, and that gives us 5. But don't forget about the units, 5 meters per second squared for acceleration. Okay, let's have a look at another example. So a car accelerates from 8 meters per second and reaches 20 meters per second in 4 seconds. I'm going to calculate the acceleration, so it's a little bit more complicated because it's not starting from rest. So we just quote the equation again. That's the initial velocity. 20 meters per second is the final velocity. And again, the difference in time, the difference in those two in terms of time is 4 seconds. So we have 20 minus 8 divided by 4, 12 divided by 4, and we've got an acceleration of 3, and again the units meters per second squared. Okay, let's have a look at another example. So it accelerates this time from 20 meters per second to 12 meters per second in 4 seconds. And now we've been asked to calculate the deceleration. So using the same equation again, and 20 meters per second is going to be the initial velocity this time, and 12 meters per second is the final velocity, so the velocity's got smaller. And that's quite important because when we do 12 minus 20 in that calculation, we get minus 8. Now that tells us that the velocity is decreased, and that tells us that the acceleration is minus 2. And again, meters per second. But the question is calculate its deceleration, and that minus sign there means deceleration. So we can get rid of it and say, actually, the deceleration is 2 meters per second squared, just to make sure that we're answering that question properly. Let's have a look at another example. So a car this time is moving at 10 meters per second. It accelerates at 3.5 meters per second squared for 8 seconds. And this time we're going to calculate its final velocity, so it's a slightly different variation of that equation. So we still quote the equation in a form that's comfortable to us, but this time we're calculating the final velocity, and that's going to be v, so we need to rearrange that equation. And again, make sure you're comfortable and confident with rearranging equations. So we've got 10 meters per second for the initial velocity, 3.5 meters per second squared for the acceleration, and we're going to calculate the final velocity. Rearrange it, v equals u plus at, substitute in the numbers, and always do it step by step in an exam, and we get a final velocity of 50, and that's going to be 50 meters per second. Never forget the units because you'll lose a mark if you don't quote the units. So that's how to use that equation of motion. The acceleration is change in velocity over time. So there's the other equation of motion that you need to use, and that other equation of motion is one of 4 that we use in physics, but you only need to use 2. So we've already introduced you to one. So this is one of the equations of motion, and v squared equals u squared plus 2as is another. You don't need to know any of the other 2 for GCSE or IGCSE. So there's lots of different terms there, so it's important that you understand what all of those symbols mean. You may, if you've done a little bit more of this, know them as the Suvat equations, but here's a list of what all the terms mean. V for final velocity, U for initial velocity, A for acceleration, and S for distance, although sometimes it might be written as x for distance, so just be aware of that. So let's have a look at an example of this, another equation. So a car starts from rest and accelerates at 3 meters per second squared at over a distance of 2.5 kilometers, and we're going to calculate the final velocity. So we write the equation down, v squared equals u squared plus 2as. And what we can do is identify all the different variables. At rest, well, that's going to be u, and it accelerates, so that's going to be a, and the distance, 2.5, that's going to be s. So we've identified all the different variables, and now we can substitute in. But first of all, we've got kilometres over there, and everything else is in metres. So the first thing to do is just convert those kilometres into metres so that we've got everything in the right units. And 2.5 times 1,000 is going to give us 2,500 metres. Now we can substitute in v squared equals 0 squared, and then plus multiplying that bracket out. Plug that into your calculator, and we get v equals the square root of 15,000, which is 122.5 123 to 3 significant figures, because all the values there are in 3 significant figures, and don't forget the units. Okay, so we'll look at a second example. So a runner's top speed during the final lap of a race is 5.3 meters per second. We're going to calculate the initial speed if they've accelerated in that final lap at 0.015 meters per second squared over a distance of 400 meters. Write the equation down and identify all the variables. Its top speed is 5.3 meters per second, so we're going to say that's going to be the final velocity, and that's going to be the acceleration, and that's going to be the distance. So we're trying to rearrange that for the initial velocity. I'm trying to remember what the question was. So we need to rearrange the equation for u, and u squared equals v squared minus 2as. So now we can plug in all the different numbers. We can do it step by step, multiply out so we don't make as many mistakes as we might do if we try to do everything at once, and get an answer of pretty much 4 to 2 significant figures, but remember the units in meters per second. So I hope you found that episode on equations of motion useful. Subscribe to the channel for other ways in which we can help you with your physics and GCSE and GCSE exams. And I'll see you next time on Spiral Physics Education. Thank you.